Swayam Prabha. Digital India. Educated India.
Or maybe after all I will use a different example. This one is too trivial or simple to find. So again let me write down this small example. So the question is, how do we find a stable matching now or report that there is none? So can you just execute the Gale-Shapley algorithm? Not considering the fact that this is or ignoring the fact that it is non-bipartite. So for example, let's just ignore the fact that this is non-bipartite and so on and try to and we'll just ask people to propose. So what will happen in that case? So suppose we start from 1 proposes to 3 and 3 accepts because 3 is currently free. Okay. So and next 2 starts proposing, 2 proposes to 4 and 4 also accepts. Now everybody is matched, so there is nothing else to do. People proposed and some people, whoever they proposed, accepted. So is this matching stable? Right. So this matching is not stable. Why? Because here 3 is matched to 1, 4 is matched to 2. So you see that 3 and 4 both prefer each other over their current partners. So this forms a blocking pair. So we tried to execute the Gale-Shapley algorithm, but it has not worked. What is the reason that it did not work? I mean, if it worked in men-women case, why is it not working here? Yes, precisely. So here 1 and 2 got a chance to propose and hence they also got their first choices. But then 3 and 4 never got a chance to propose and they are the ones who are blocking the matching. Right? So we should find some way in which everybody will get to propose. So an obvious thing that we can do here is when 1 proposes to 3, yeah, so here we are not getting a stable matching. Just blind Gale-Shapley doesn't work. Okay, so let's see what we can do. Okay. So let's look at this and what we will say is when 1 proposes to 3, 3 should not be made to commit to 1. Right? That is what we want. 3 should still get a chance to propose. So we will make these engagements or temporary acceptances one-sided. So when 1 proposes to 3, 3 holds that proposal and says, okay, I will consider if I don't get any better match. But right now I will only keep you on hold. That is what 4 will also do. These are called as semi-engagements because they are only engagements from 1 and 2. So 1 and 2 are not going to propose to anyone else unless they are rejected by 3 and 4 respectively. So these are the commitments from 1 and 2, but they are not full commitments from 3 and 4. They are still going to propose others. Okay. So these are semi engagements. Or partial engagements. So okay, now we have decided that 3 and 4 are allowed to hold these proposals, but they are also allowed to propose further. So now 3 proposes to first person, that is 4 on his list. 4 accepts. So what we will do is, we will do a small modification of the proposal and rejection algorithm. So whenever someone, so now here for example 4 has got a proposal from 3. In future will 4 accept a proposal from 1 or 2? There is no chance that 4 is going to accept a proposal from 1 or 2. So we will just put a cross on them. 4 will delete them from his list. Because it is just useless to keep them. He is not going to accept proposals from them. If at all he gets a better proposal, in this case it is not possible, but even if there were some people before 3 in his list, he would have considered those proposals in future, but not someone worse than 3. Right? So 4 just deletes these people, and hence mutually they are also deleted from their lists. 4 and 4. Right? And here now 4 got a better proposal from 3, so 4 is going to break this semi-engagement. Now 2 has to go ahead and propose, because now 2 doesn't have any promise from anybody. So 2 has to go ahead. Now 2 will propose 3. 3 is holding a proposal from 1. So between 1 and 2, how does 3 compare? So 3 prefers 2 over 1. So 3 is also going to break this engagement or this commitment and will accept 2. So remember that when a person making proposal versus a person receiving proposal are disjoint. 3 has proposed to a better person 4, but 3 is also holding a proposal from someone else. So this one is an incoming proposal for 3, whereas this one is an outgoing proposal. Okay. So the incoming, if at any point every person has at most one incoming proposal and at most one outgoing proposal. So this is, so at any point, maybe I should write somewhere else. This is the crux of the algorithm, that at any point each person has at most one incoming and one outgoing proposal. So let's see where this algorithm ends. So now 3 has accepted 2, and 3 is never going to accept a proposal from 1 again, because 3 already has a better incoming proposal. So 3 deletes 1, and hence 3 is also deleted from 1's list. Okay, so 4 has not proposed yet, right? The proposals have all been from 1, 2 and 3. 4 has not got a chance to propose. Let's give a chance to 4. So 4 will of course propose to the first person, that is 3. Right? So 4 has started proposing now. Natural thing for 4 is to go to the first person, which is 3. So 3 is currently holding an incoming proposal from 2, but now 4 is more preferred to 3. So 3 will indeed reject this incoming proposal, and hence also will delete 2 from the list, because now 3 holds a better proposal. So what are our new lists? Who all are remaining in 1's list? Only 2. And what about 2? Only 1. Now 3 also has only 4 in his list. 4 also has only 3 in his list. Can you identify a matching now? Now the matching is obvious, right? You match 1 to 2 and 3 to 4. Now is this stable? It is. So just giving a chance to everyone to hold an incoming proposal and simultaneously make a proposal to others, has it worked? Okay, so I assume that this algorithm is indeed clear. What happens if we execute it on the first example that we had, where we did not find any stable pairing? So, okay, I'll just rewrite this example. So this was our example where we did not find any stable matching. So let's see what happens to our algorithm when we execute it on this. What will happen? What is the guess? So now can you try executing the same algorithm on this? Say it again. Yes. So if you execute it, which I will quickly show in case. So again here 1 will propose to 2, 2 will hold this proposal but will still go ahead and propose to 3. And now 3 will propose to 1, which 1 will not accept. Sorry, 3 will propose to 1 and 1 will hold it. Well, so 2 has received a proposal from 1, 2 is not going to accept a worse proposal. 3 has received a proposal from 2, so 2 is also not going to accept a worse proposal. Now 3 has proposed to 1, so 1 has also one incoming proposal from 3 and 1 is not going to accept another proposal. So 4's list becomes empty. So what happens is 4's list becomes empty. Which shows that 4 has no stable partner, so there is no stable pairing. Whoever you match with 4, that person wants to go to someone else. And also that some other person is willing to accept that. Okay. So this is a small claim. At the end of the algorithm, if someone's list becomes empty, then there is no stable matching. And the other case was when everybody has only one person on his list and being on the list is mutual, as in we keep I on J's list if and only if J is on I's list. So that directly gave us a matching. So this is one thing and this is another one. At the end of the algorithm, if everyone has just one person on his list, then we get a stable matching. Yes? Very good, yes. Conversely, if there is no stable matching, oops, sorry, matching, then someone's list will be empty. Yes? Yes, so if there is an odd number of people, then we cannot hope to pair them up at all, right? As in there has to remain one person. So I mean the interesting case is when there are even number of people and still we are not able to pair them up. So we will assume that we have an even number of people, otherwise we are compelled to give a single room to one of them. So that person doesn't need a roommate. So I will write down this assumption. Number of people is even. Okay, so in one of the examples, one list became empty, and in the other example, we actually got a single entry in every list. So we got a matching and it happened to be stable. So I have not written the formal proofs for these claims, but I think they are not very difficult to write. So you can think about these proofs, and I will move ahead little more in the algorithm and see, I mean, address a different question in this algorithm. So are these the only two cases? Either some list will become empty or every list will have just one person. So the question is, can the algorithm terminate with some lists, I mean some people's lists having more than one person? So do you think this will happen, or we will always nicely get either empty list or one entry? Yes. So the proposals are like that, but other have to be deleted, right? As in it may happen that person 1 doesn't receive a proposal from some people, but they don't also get deleted from his list. Right? We are only deleting people who are, so whenever a person receives a proposal, so I receives a proposal from J, I is allowed to delete only people after J in his list. But it may so happen that I have some person K before J, so I cannot delete. So like this. So here is I's list. I receives a proposal from J, so I crosses out everybody here. But then if there is a K here, I cannot cross out K. At the same time, there is a possibility that K receives a better proposal and K crosses out I. But even that may not happen. So we will see an example now where we don't nicely get this one entry in each list, and we'll end up into a more complicated situation. So this is a slightly bigger example because the 4 size examples are a little trivial. I think this is example 4. So there are 6 people, so I will write all the 6 lists. So typically when we design an algorithm and we see it working on a few examples, we tend to believe that it is correct and complete. But one has to always look for counter examples, and this will give a counter example to our belief that we always end up with either an empty list or singleton lists. So now can you execute the algorithm and tell me what all lists you get? So I will also start executing for myself. So 1 proposes to 4. 4 for now holds the proposal, but then 4 crosses out everybody after 1. So 3 goes from 4's list, 4 goes from 3's list. Now 2 makes this, 6 also holds it and do the similar crossing out, that is crosses out everybody after 2. Now 3 has already 4 crossed out because 4 has crossed out 3. So 3 has to go directly to 5. Now 5 again holds this, but then crosses out 6 and 1. What else? Now there is 4. Now 4 goes to 2. 2 holds it. 5 has not yet proposed. So 5 goes and proposes to 4. Yes. Yes. So 4 has currently accepted a proposal from 1, but 4 prefers 5. So 4 will accept this and reject the proposal of 1. Now there is 6. 6 goes ahead and proposes to 1. 1 has no proposal so far. 1 accepts it and crosses out 2 and 3. And 1 doesn't have an outgoing proposal now. So 1 goes ahead and proposes the only person on his list, which is 6. Now 6 prefers 1 more than 2. So 6 rejects 2's proposal and accepts 1's. And because 4 and 2 come after 1 in 6, the list of 6, 6 deletes 4 and 2. So then 4 and 2 also have to delete 6. Sorry, 1 has crossed 2, so 2 also has to cross 1. And then 1 has 3 crossed, 3 also has to cross 1. Okay, so these are the final list that we get. 1 has only 6, 2 has 3, 5 and 4, 3 has 5 and 2, 4 has 2 and 5, 5 has 4, 2 and 3, 6 has only 1. Okay, so the algorithm now has finished because everybody has one outgoing proposal and one incoming proposal, and these are the lists the algorithm has written. Actually, one more I have not shown, where 2 should have proposed 3 because 2 has no outgoing proposal and 3 has no incoming. Yeah, so here it will terminate. Sorry? Yeah, so 2 should have been crossed. No, 3 did not have any proposal, right? Okay, so here we had not been fortunate enough like last time where every person had only one entry in the list. So from these lists, can we recognize a stable matching? Yes? No, so this happens only when one receives a proposal. So when 2 proposes to 3, we should cross out people from 3's list who come after 2. But then there is nobody in 3's list after 2, so we did not cross out anybody. See, even though 2 is proposing to 3, it is not clear whether 3 will eventually reject 2's proposal. So 2 should still retain later options. Right? So what happens if we simply choose a matching by inspection? So is this stable? Yes. So here we see that, sorry, I should put more blue circles. So 3 is matched to 5 and 2 is matched to 4. Okay, so we see that 2 and 5 both prefer each other over their current partners. Why? At what point did you delete 5 from 2's list? Sorry, say it again. It never happened, right? We see these proposal sequence. We see this proposal sequence. They have never proposed each other. But uh, but it never happened that 5 received a better proposal than 2, and 2 also never received a better proposal than 5. Yes. So deletions happen whenever someone receives an incoming proposal. That someone is allowed to delete everybody after that. So some deletions don't happen simply because those people don't approach each other and they don't even get approached by better people. So if you see here, 5 had got only one proposal which was from 3, but then 5 prefers 2. So 5 did not delete 2. But then, yes? Oh. Yes, so let's mark this other matching. 1, 6. See, clearly 1 and 6 have to be matched because they don't have anybody. Ambiguity is about only those people. So is the green matching stable? It is, right? But then it is not clear how to extract the green matching over the blue matching. Right? So if we just look and try to extract out a matching, we may extract out the blue matching and may not extract the green matching. So at this point it is not clear how to extract a stable matching at all, because some matchings here may be unstable like the blue one. So here we actually need a little more work. So intuitively this green matching will come into picture if we just force 3 to, or rather force 5 to reject 3's proposal. Okay, so we just force 5 and 2 to reject proposals of 3 and 4. See, 5 and 2 won't be terribly unhappy because anyway these are the last people on their list. So 2 rejected 4's proposal, 5 rejected 3's proposal. And let's see what nice effect it has. So what will 3 do now? So somehow magically 5 was forced to reject 3's proposal. So 3 will naturally go ahead and propose 2. Right? So because 5 has rejected 3's proposal, 3 got crossed out from 5's list. So 5 should also get crossed out from 3's list. Okay. So now 3 will go ahead and propose to 2, and similarly 4 will go ahead and propose to 5. So in fact, yeah, so now 2 receives a proposal from 3, this one. So 3 is in a position to cross out 5. Similarly, 4 gets a proposal from, no sorry, yeah, so this is mutual. And now magically we have just one entry in each list. Right? So if you look at the remaining entries, now you get a nice matching. So some artificial rejections of proposals, and then you have ended up with one entry in each list, which gives you a stable matching. So it looks something out of the blue why you should propose, why you should break some engagements artificially, but nevertheless it works. And how to choose the engagements to be broken, that is the only thing. So in a couple of minutes, because we don't have really time left, but in a couple of minutes I will tell you how to choose breaking the engagements to break. So any question here? At least what we did, is it clear? How we did or why we did is not clear, I understand, but at least what should be clear. So what we want to do is, we want to find cycles of this form. So we want to find people that have multiple entries on their list. So suppose A has B1, B2. Now we want to find another person who has B2 as his first choice. So suppose that person is A2 who has B2 as the first choice and maybe some other second choice. Okay. So find people of this form. Although I am writing A's and B's, they are not men and women, they are people of the same type, either all boys or all girls, for whom we are trying to find roommates. These are just the names that I have given. Somewhere this cycle, this will complete. So again we look at the second entry in A2's list and find an A3 so that A3 has that entry as the first choice. So B3 appears at the second place in A2's list. We look for an A3 so that A3 has B3 as first choice. And somewhere this will end with A3 having B1 as the second choice. So this has become cyclic. Each AI has BI as the first choice and BI plus 1 as the second choice. So if you find this kind of cycle, you can break these engagements forcefully and these people will go ahead and propose the rest. So once you find a cycle, so here for example I produced a cycle A1 of A1, A2, A3, in that cyclic order they have their preferences. So I just so clearly B1 appears first on A1's list, that means B1 is holding an incoming proposal from A1. So that engagement I break. So choose any such cycle and break the engagements in that cycle. It is not 3, 4, 5, right? So let's try to find a cycle in this example like that. Okay, so I choose, let's say 3. 3 has the list 5 and 2. Next, I want to choose a person who has 2 as his first choice. Now, who is such a person? 4 had 2 as the first choice, right? In this list which came at the end of the algorithm, not the original ones. So 4 had 2 as the first choice and next choice was 5. So we have completed the cycle because again this is the first choice in 3's list. If this was not 5 and someone else, this procedure would have continued. So we just take some person's preference list, look at his second choice, find another person who has that as the first choice, again look at that person's second choice, find yet another person who has that as the first choice, and so on. So this will sometimes stop because the number of people is finite, and then we will get a cyclic situation like this. And once we detect this cycle, we decide that these are the engagements we will break. So I am not completing the proof of this or not even sketching this, but what one needs to show is that if there is a stable matching, that has all AI BI pairs, then there is also one without them. Okay, so this forceful breaking of engagements may cause us to lose some stable matching. What we need to prove is that there is yet another stable matching which we are retaining. And also another thing to note here is that any stable matching either has all AI-BI pairs or none. So these are the things which need to be proved. Which I am not proving at all. So nevertheless, with these claims left unproved, you can possibly prove them or you can look up for the proofs, but we really don't have enough time to go over the proofs. So I will stop here. I hope you have got a glimpse of the non-bipartite setting, and you see that the non-bipartite setting certainly becomes far more complicated than the bipartite one. And nevertheless, it is an interesting setting, it is a realistic setting, and hence one needs to study this one as well. So again, thank you for being attentive and being present here. And I really enjoyed giving talk here. Is there a cycle between 2 and 5? Let's see. No, not last, first and second. So if you consider 2, you need to consider the first preference 3, second preference 5. Then find someone who has 5 as the first preference, which is 3. And then 3's second preference is 2. Now look at again someone whose first preference is 2, that is 4. So the cycle again completes within these people and 2 doesn't come into picture. Say it again. It can be arbitrarily large. This cycle can be large, but eventually it will complete. So even if we start from 2, we really don't have a way to include 2 in the cycle because it only completes at 3. I mean only 3 and 4 appear in the cycle. We always have? Yes. So there is always one cycle. We are not guaranteed that because we have ended up with non-empty list, we have a stable matching. When we do this forceful breaking, we may end up with an empty list, in which case we will still conclude that there is no stable matching. So there exist one or more cycles, and after breaking the cycles repeatedly, what I mean is we will break one cycle, still we will have multiple entries and more cycles and so on. After breaking the cycles forcefully, we may end up with an empty list, which implies again no stable matching. So what the proof guarantees is that if there is a stable matching with these particular list, then there is one after forceful breaking of engagements as well. So if we end up with not having a stable matching, which means it did not exist in the first place. So yes, so such a cycle definitely exists. So you start from anybody, look at the second entry. So for example here 5 is the second entry. Why should there be anybody who has 5 as the first choice. Now, an interesting thing to observe here is that if someone is, as in if here for example 3 is 2's first choice, so 2 is 3's last choice. So here for example if you look at this 2's list and 3's list, you see that 3 is the first choice of 2, but 2 is the last choice of 3. So this is not a coincidence, this is what will happen, the way we are deleting entries. So if I is the first choice of J, J is going to be the last choice of I. So same thing you see for 4 and 5, that 5 is last in 4's list, 4 is first in 5's list. So this is not a coincidence, but this is also a property of the algorithm. So you can use this property to say that there always exists one such cycle. So unfortunately I cannot complete the proof because it will still take much more time, but I will certainly mail the paper to you and you will see the proofs of these claims. Each of the proofs is small, but there are many small things that one needs to prove. So thank you. Any other question? Okay, so thank you, and this was my last talk. So enjoy the rest of the school, and hopefully you will have some takeaway from here.